Good Tuesday to you, everybody in COM 702. Welcome to week boom 4. How's everybody doing? All right, now we're getting into some of the funner stuff as we take a look at various quantitative research methods and statistical concepts. So buckle up, boys and girls. It's going to be an interesting ride, and to get us ready, let's mm, shortwave coffee. One of my favorite local coffee shops. Very cool cat that owns that coffee shop. So now here I am back again, Dr. Jeff Gardner, your sufficiently caffeinated communication instructor, with a review of last week's forum. That is forum number 3 during this week 4. Okay, a couple of items before we get rolling. Last time you may recall that in my video I mentioned, this was a little lozenge to moisten my throat. This would be a good time, and that was 2 weeks ago, to start drilling down on your research papers. Now, a number of you have emailed me and said, how's this by way of research topic, or even some of you email me and say, how do I start? I'm not quite sure, and so on and so forth. Let me suggest you do it like this. Be good to yourself as a researcher. Okay? Start with a hypothesis or a combination of hypotheses and research questions, because in this class, you could just have a research question, but we're really trying to get you to think about and to be able to research causation. That is, the one thing causes the other, okay, and not just correlations. One thing's happening and then this other thing is happening at the same time. Well, but it doesn't mean that one is causing the other. All right. So be good to yourself as a researcher and start with a good hypothesis. Now, remember that a hypothesis has 3 essential elements. All right. Number 1, it has at least 2 variables. Now, let me encourage you at this sort of stage in what you're doing, because remember, a lot of what we're about this semester is you learning the tools, right? And that takes some time. So keep it straightforward, okay? It has at least 2 variables. The hypothesis makes a prediction about the causal relationship of one variable to the other. For example, one variable number, remember, a variable is just a thing or an occurrence, anything like that. Variable number 1, hot cup of coffee. Variable number 2, how burned my leg is, because right now it's not burned at all. Okay, prediction of causal relationship. The amount of hot coffee I pour on my leg is positively correlated to how burned it is. Okay. And by the way, when you're formulating this relationship as part of the hypothesis, avoid the obvious. Okay. Like the more hot coffee you pour in your lap, even if you get it from McDonald's, the more burned your lab is going to be. All right. So that's, number 1, at least 2 variables. Number 2, there's a causation that you're predicting. A hypothesis is you're making a prediction about something. And number 3, there is a direction of this prediction. That is, more hot coffee leads to a sensation of burning, not a sensation of burning leads to me going to get more hot coffee, which sounds a little, sounds ridiculous, but you get what I'm saying. You're saying that this phenomenon has just the one direction. So start by formulating a hypothesis that has 2 variables, predicts, you're making a prediction, okay? A relationship, a causal relationship. The more of this, the more of that, the less of this, the more of that, the less of this, the less of that, or whatever. You're predicting a causal relationship. And it has a direction, okay? If you sit down, and get to your think space, wherever that space is for you, whether driving in a car, sitting, drinking your coffee, spending a little time, composing your thoughts. I mean, I will tell you that for my part, I'm no fan of the early morning. All right. But on a regular basis, I get up early in the morning and I sequester myself. That is, I just turn off my phone, I close my office door, and I lock it. And I do nothing. And I do this in the morning. I try to block out at least an hour, usually two. And I do nothing but write during that time. All right. So that's sort of my think space. So get to wherever your think space is and start with a strong hypothesis that has those three elements. And that's going to do a lot for you as a researcher. First, it's going to limit your focus. Because remember, all research has limitations, and the two limitations that all research has are time and access. How much time do you have to get to the material you need to do the research? And neither of those are limitless. Not even for professional researchers. No, and you've got to, sometime around the back end of April. And that's it. And it's, let's just call it February. I mean, today's the 31st, but okay. So in putting together a strong hypothesis, this limits your focus. So you're going, okay, I'm really interested in all these other things over here, but I'm just going to look at these two variables, a predicted causal relationship that runs in this direction. And all of the other stuff that's involved with the topic that, this pertains to, that can wait to the next study, to the next paper, whatever. So first and foremost, a good solid hypothesis limits your focus, which is good for you, being good yourself as a researcher. Secondly, a good solid hypothesis is absolutely key. It will help you so much in writing your survey instrument, putting together your survey. Because, for instance, let's say, here's my hypothesis. I'm got a little bit of a sore throat, so I'm chewing on these curiously strong Altoids. So what if I say, I've got a couple of dogs too in my house. So what if I say, the more I shake these Altoids, the shaking of these Altoids is positively correlated to my dogs coming to find me. All right, that's my hypothesis. Now I could have it the other way around. My dogs coming to find me is positively correlated to my shaking of these Altoids because, clickety-clackety sounds when done like that sometimes irritate dogs. And I don't want the dogs to find me because I'm sequestered away doing my writing. But in this case, we're having it to go, that way. That's the direction, okay? Two variables, my shaking the Altoids box and my dogs. Predicted relationship, the more I shake the box, the more dogs I get, okay? And in that direction. All right, now, how does this help me devise my survey instrument? Well, if I want to test a causal relationship, this causing that, okay, what kind of data do I need? Could I just get by with categorical data? Like count the number of times I shake the box and then just, count the number of times the puppies show up and go, oh, well, here's the averages. Well, that will show me correlation, the average number of box shakings and the average number of dog sightings, but it doesn't suggest causation. We're going to get into, a type of test called a regression analysis that will let you show causation. And don't let the title throw you. It's really no more complicated than a t-test, both to enter into SPSS and read the results. It really is not. But unlike a t-test, it's going to show causation. All right. So I'm going to need continuous data. Okay. So I'm going to have to design a certain type of question, like something with a Likert scale that gives me continuous data. So when you put together your hypothesis, this is going to first of all tell you what type of questions in terms of structure you need to have on your instrument, your survey instrument. And then secondly, what kind of questions do you need to ask? Let's say, for instance, you wanted to, take a look at how frequently somebody watched football. Now that, playoffs are finished and we got 2 weeks to the Super Bowl, but don't fear not. The NFL has plenty of content, especially if you want to pay for the app. So how much, how often they watched football and what what they thought of their marriage. Strong from weak, don't know, too strong. Okay. All right. So you construct a hypothesis that had two variables, predicted a causal relationship between the two, and had a direction. Let's say the amount of football watching is inversely related to the strength of a marriage. All right. Unless, of course, both couples are football fans. There's the more football somebody watches in a relationship, the weaker the marriage becomes. I'm not saying that's the case. I'm just saying, hypothetically, hypothesis. Okay. All right. What sort of questions, now, aside from type, like Likert scale, do you need to ask? Do you need to ask questions about watching basketball? No. I mean, if your hypothesis concerned all sports watching, yeah, okay, fine. But you're just looking at football. So you need to come up with questions that pertain to someone who watches football. How much time do they spend? What do they do before? What do they do after? Do they interact with their spouse? Do they exclude themselves from family get-togethers, and so on and so forth? So a strong hypothesis limits your focus and then helps you focus, guides you in the writing of your survey instrument. Okay. And then finally, and this is the third and perhaps most major benefit to you as a researcher, this is how you're being good to yourself in limiting your focus and then sort of drawing and narrowing down the types of questions you have to ask. You can eliminate a whole bunch of stuff that you don't have to talk about when you do your literature review. All right. And that's, once you come up with a survey instrument and take your time, okay. And by the way, look for examples. I mean, look in the published material from Dr. Brown, or look online and look at my stuff, or the Regent Library. Look at my dissertation. Okay, look how the survey is constructed. Okay, that this narrows down what you have to do in your literature review, because once you figure out the survey, writing the survey, running the survey, putting the data into SPSS, that doesn't take long at all. And by the way, the good news is with something like SPSS, it takes you as much time to analyze once you put the data in, to analyze the output from 50 respondents as it does 50,000. It's just numbers at that point, right? The real time vampire, the thing that just sucks time and demands your time and effort, is the writing of your literature review. Okay, so be good to yourself as a researcher. If you're not sure what you're doing with this paper, start with a strong hypothesis. That strong hypothesis is going to limit your focus. It's going to show you the way to building a strong survey instrument, and both of those are going to narrow the scope of what you have to do in your literature review, all of which adds up to a smoother research / paper writing experience for this class and beyond. Okay. So a robust and clear hypothesis is your best friend, is your king. Okay, let's take a look at the questions and answers from week 3. You did very well, most of you. A couple of things I want you to pay attention to when you read these questions, because the demands, if that's the right word, of these questions may appear again, say, I don't know, like a final exam, a wink. All right. And you want to make sure that you're able to answer it. So, for instance, question number 1, in what situations would you use a one-tailed t-test versus a two-tailed t-test? Okay. Many of you correctly wrote the definition of what a one-tailed t-test is as opposed to a two-tailed. And by the way, I'm looking for something to write right right away, but I don't seem to have something nearby. You know, if you're having a hard time sort of like, okay, because you are memorizing a lot of new terms, how you keeping this stuff straight? Think of tail as like a, you know, an arrow, a line, like, Sarah, maybe I got something here. Let me just see. Sorry. Here's an article that I'm reading. Here we go. So think of useless. Think of tail. All right, like a little pointy tail. There we go. That's what I'm looking for right there. Okay. So here's how you know, little mnemonic device to help you remember just that bit of jargon. Okay. So one tail, sort of one little, it's moving in one direction. Two tail, both sides, right? Going both ways. One tail, two tail. Okay. So anyway, back to the question. The question was, in what situations would you use a one-tail t-test versus a two-tail t-test? Many of you defined one-tailed and two, but you didn't answer the question of why you would use this. Okay, so Carissa, I'm going to pick on you just a teeny little bit. You say, Phil states that the test or hypothesis can be either directional one-tailed or non-directional or two-tailed. Directional hypothesis states that an effect will occur, but also states that the direction of the test, of the effect. That's me. On the other hand, a non-directional hypothesis states an effect will occur, but doesn't state the direction of the effect. Okay. From what I can gather, this is what you write, Lewis. I like this. From what I can gather, they are both used for data, but the outcome and the direction of the outcome and the direction of the effect change what kind of data. Yeah, okay. Can you be a little clearer? Yes, they're all used for data, but why? Okay, so Amanda, one-tailed t-test is a directional hypothesis, or maybe the way to put it in, you know, proper order. One-tailed t-tests are used with directional hypothesis. A two-tailed t-test is used with a non-directional hypothesis. One-tailed t-test would be used when a researcher wants to determine if there is a difference between groups in a specific direction. This is appropriate if the estimated values depart from the value in one direction. For example, when you look at a machine that produces a toy, a researcher would use a one-tailed test to find if it produces more than 1% defective toys. Perfect, because defective toys aren't producing machines that produce defective toys, but you get what I mean. Okay. A two-tailed test would focus on the possibility of a positive or negative difference within the research. For example, if you have two different machines producing two different toys, a researcher will use a two-tailed t-test to see if machine A scores higher or lower than machine B. Okay, so not in the sense of the toy to the machine by way of direction, but this machine and this machine. Okay, so look, you know, make sure you look carefully at the question again. A wink, and you know what we're really getting at is why, you know, by being able to explain why you would use it, it's implied, we assume, that you'll understand what it is. Okay, so make sure you're able to answer that. Okay, question number 2. What's the difference between type 1 and type 2 errors when testing hypotheses? You hear this terms, I should say type 1, type 2 terror all the time. Timothy, I like what you're up to here. And good afternoon to you too, sir. You cite fields. A type 1 error occurs when we believe that there is a genuine effect in our population, when in fact there isn't. So we call this a false positive. Okay. What this entails is that there is less than 5% chance that the overall population is affected. In other words, we have not hit that, you know, more than 5% threshold. Now, how can this occur? You might ask. Lots of ways. Maybe you had bad data. Maybe you had outliers that skew the data that are not representative of the mean. Okay, there's a lot of things that can drive a type 1 error. Maybe you keyed it in wrong. I don't know. I mean, this happens. I'm not saying just you. I've done this too. Okay. The opposite is a type 2 error, which occurs when we believe that there is no effect in the population, when in reality there is. An example of this might be when we sample a rather small batch of data from a larger group, and it visually appears to be the case that the data is not impacted. However, after viewing a larger group, it evidence that it is. And by the way, this could be one of the causes of a type 1 errors. The sample size is just too small. Because, say, if you wanted to figure out what 10 million people were doing, let's say you're looking at, I don't know, that would be a big state. Do we have any states with 10 million? Maybe California. Okay. But with people across the whole state were doing, and you sampled like 10 people. You, aha, look, look at this amazing p-value that I've got here. Everybody, this is the statistically significant trend that the majority, the means of the people are doing. Because you're overstretching, you're overprojecting your data. Type 2 error runs in the other direction. That is, that we believe that there's not an effect when in fact there is. So maybe we did sample enough people, okay? But again, we entered the data wrong. We didn't look at a random sampling, and we miss the fact that I don't like that expression. The fact is, we miss that there is a statistically significant effect going on. Okay, type 1, type 2. Okay. Amanda, did I do you last time? Yeah. You know what? I'm going to pick on you just a teeny weeny bit. Type 1 error, et cetera, type 2. Okay. For example, the medical test states that a person does not have coronavirus, but does, and that's your example for type 2. If a person's test results say they have coronavirus, but they don't, that's a false positive or type 1. Okay. That's true. And in that kind of test, the same verbiage is used. I guess I'm not really picking on you. I wanted to use your answer to make a point. True, but I want you to be aware, all right, of the difference between, say, a mechanical failure of a test, say, like, I don't know, pregnancy strips, all right? Because they or some of these, or like COVID tests, some of them, they have expiration dates, or they have temperature ranges because they're detecting enzymes, they're detecting proteins, they're detecting hormones. And if the thing that does the detecting is out of date or it's been damaged and you have a false positive or a false negative, that's not the same as reading data, handling data, processing data, inputting data is. Okay, so just and Amanda, your answer was just fine, but be aware of that by way of differences when we're talking about statistics versus, say, the mechanical operation of a thing like a test. Okay, question number 3: how is a z-test related to a t-test, and in what kind of situation would the z-test be useful? See, this is another one where a number of you correctly define the difference between the z-test and t-test, but what you didn't do was tell us why would you use this one as opposed to that one. Okay, so as a give back to you, I know I poked at you a little bit for that last answer. Let's go back to you, Amanda, because did you see that the answer that she put up? She put up a really useful chart. So if you didn't look at that, go ahead and look at that. And did you put the link, Amanda, as to where you got said chart? Yes, you did. Okay. So, all right. So let's go back to the question. So Amanda, you're right. Overall, okay, so you have like the box and then you have the chart. Overall, this chart shows the difference in connection between z-test and t-test. Both of them are types of tests. Focus on 2 data sets. However, they differ in that the researcher would use one or the other, which, okay, yes, true. When I was trying to figure out what situations a t-test would be helpful to, I found this image from Data Analytics website. This graph is beneficial to quickly figure out which one researchers should choose when working with a data collection or collected data, if you like. Okay. So if you don't know the population standard deviation, okay, use a t-test. Now, why are we concerned, obsessed with standard deviation. Because remember the couple of videos back, I gave you the example that if you were a kindergarten teacher and you wanted to find out how many times within a span of time a 5-year-old could jump up and down, let's say 60 seconds. And so you line 10 of them up and you were going to have them, you're going to say, okay, go. And you're going to hit the stopwatch and you're going to count the jumps in the 60 seconds. All right. If you repeated that with a number of kindergarten teachers across the nation in different places, all right, there would be, the mean would be sort of here as opposed to there, but there would be a range, a deviation range that becomes standardized. If there's something outside of that range, that's an indication to you that there might be a problem here. All right. Now, remember back to our example. Maybe the problem was among the 10 kids that you lined up, there were 3 or 4 of them that just said, oh, I ain't playing this game. And they refused to jump. Now, it's a legitimate question. Can you get a 5-year-old to jump up and down as many times as possible in 60 seconds? That could be an interesting study, but that's not what you wanted to do. You wanted to see what is the average number of jumps per 60 second. And if you've got like 3 or 4 who refuse to participate, that's going to skew the results. So we look at standard deviation, okay, because we want to make sure that we're within this range and there's not something funky going on there that whacks out our results even before we get to the analysis, because you really can't get at questions of like causation with bad data. Okay, so first question, do you know the population standard deviation? If the answer is no, use the 2 tests. If the answer is yes, then what's your sample size? Because remember, as the sample size drops, just for the kicks of it, take that data set that we gave you in lab 1 and duplicate the file. All right. And then that duplicated file, delete half. And then duplicate the file and delete half again and half again. So you have like 3 or 4 files that are exponentially smaller each time than the other. And go ahead and run the t-test. Okay. Now, ratio-wise, you're going to get things that are very similar in terms of p-values and these things. Watch. Well, no, I should say I'm not going to tell you, but watch to see what you get. But as the number goes down, the sample number goes down, the power of the external validity goes down. All right. So there you want to use a z-test. Okay. All right. Question number 4. Why should a p-value always, in capital letters, be reported with statistics? Cassiopeia. One reason why p-value should always be reported is, quote, it gives the reader more information than simply knowing that the p-value was less or more than the random threshold of 0.05. Okay, that is absolutely right. But remember, it's not a random threshold. Okay. Yeah. You can, depending on the research, the type of research that you do, your tolerance for error goes down, because 95% or 5% tolerance for error, that's about the bare minimum. Remember the coin flip video? If you flipped a coin 1,000 times or 100 times, and you flipped it 10 times, 100, and you mark down heads or tails, you say you put 10 groups. So my first flip of 100 times, this many heads, this many tails, second, third, fourth, this like that. Okay, that you would expect a normalized distribution split between heads and tails to run at 95% or above. If it's not, there's something going on here. Maybe it's a trick quarter. One side's heavier than the other. Maybe you are making mistakes in writing down heads or tails. Maybe you get someone to help you so you don't have to keep putting the coin down and picking the pen up and making, recording its heads or tails. So you're calling out heads and tails. Maybe that person's been getting it wrong. There's some force acting on the outcome of what's going on than just the random force that drives the coin to flip. Now, when you look at tests, if you look at the statistical, experiments and tests in the medical field, they typically have a much tighter error range, 2% or less. Why is that? Because let's say, for instance, you're putting a new drug out on the market. You cannot have up to 5% of the population, like growing a third eye or a second limb out of their chest or some sort of crazy side effect, because you're going to get sued into oblivion. If that's the case. Well, you're not going to get past FDA unless you're making a vaccine for a certain condition. And you're not going to get immunity from prosecution or from legal liability unless you're making a certain vaccine. Your range of acceptable error has to be much, much smaller. So it's not entirely random. Sorry, Cassiopeia, but I think I know what you mean. Okay. However, Field did note that if the p-value is less than 0.001, so in other words, this is like, what would it be, like 99.99%. Okay. Reporting the p-value as p-value less than 0.11 is acceptable for the sake of space and everyone's sanity. That is perfectly. Okay. And then you add stats are not statistically significant and still can provide important stats that are not statistically significant, provide important information regarding effect, which is true. Just because something is not statistically significant doesn't mean that you're not getting a report or information about something going on. I mean, when we ran the t-test, for instance, on, if there was any difference in the means between the number of times somebody watched a social media site, participated in a social media site, an SMS, and the strengthening of their faith. Was there any difference between men and women in terms of the means? And there was no statistical difference. But that doesn't mean that what we found there wasn't interesting, because we can look at the averages for both men and women in how many times they're going to SMS and saying that their faith is strengthened. That becomes useful. Okay, that can be part of what you report on in your study. So just because, the phrase not statistically significant in this case from the t-test comes up doesn't mean that you don't have important information in front of you. Okay. Okay. So, you could, you could think of the p-value of the gold as the golden snitch, because I'm thinking of Fields of statistics. And then, no, I'm not a gigantic Harry Potter fan. Even though I'm 6 foot, I try not to be too gigantic. But that just sort of occurred to me as I was making the video, going, yeah, it's that one little thing that elusively buzzes around and everybody's trying to catch. But it's not the only way, and it's not the only thing, the only way to play the game, and it's not the only thing that's important in the game of statistics. Okay, yeah, that's a horrible analogy. Anyway, all right, everybody, the 30 minutes are up. Have a wonderful, wonderful week. I don't know what it's like where you are, but where I live, it is cold. So stay warm. I think about you a lot. I pray about you a lot. I'll look for you on Blackboard. Remember, please get on top of those topics for your research paper. And yes, of course, we want to be able to help you, but here, don't email me or Dr. Brown until you've wrestled with that hypothesis. Not that I don't want to talk to you, but part of the process of you learning the process is you learning the process. And that involves a little struggle. That's okay. We're region that we're designed for the struggle, and you're going to do just fine. All right, everybody, thinking of you, praying of you. I will see you on Blackboard. God bless. Bye-bye.